get started.
All right, so our speaker today is Erin Carmody, and she's currently at Fordham University. She got her PhD from CUNY under Joel Hampkins, so she's my academic sister, and we are very happy to have her back at the CUNY Set Theory Seminar after several years. And Erin is going to speak about the relationships between measurable and strongly compact cardinals. Go ahead, Erin.
Okay, thank you, Vika. Thanks so much for having me, and I'm very happy to be here. And it has been a long time since I've given a set theory talk, so I'm really, really extra happy to be here. And especially at CUNY, because I really love it here and I miss it. But now we're back. So so this talk is going to be two-part talk, and the first half is like the first 35 slides or so, and then so it's all contained on these slides. But okay, and this is with Victoria and Arthur, and so maybe this should be New Jersey logic, but this is work in progress. Okay, so I don't have it full screen, so I can write on the slides a little bit. So I had a lot of positions since I left CUNY. I was at Nebraska Wesleyan and then Emory, and now I'm Fordham. And so, but all very teaching positions. So then I decided I wanted to have a postdoc, but I didn't have one. So I made my own postdoc. This is on my wall. And it's called the Strongly Postdoc. So I actually work as an adjunct at Fordham and do some other things. But so I'm very interested in strongly compact cardinals and measurable cardinals, and also Hausdorff gaps. Those are just my favorite things from what I studied. And so if anyone ever wants to collaborate or have any ideas, these are the topics I like the best. And we'll see that you can't talk about strongly compact and measurable necessarily without also talking about super compact. So we'll talk about super compact today too. And I just want to say, feel free to, if you have any questions or if you have any comments or any anecdotes. I love anecdotes. Yeah, so this is the large cardinal diagram. So just kind of say where we are today. And this is, we're here strongly compact and measurable, and see how the relationships between them, specifically, we're going to be talking about Mitchell order. And we'll see that we're going to be talking about super compact too. Because these are all very actually closely tied together, and still we don't know how closely tied. Sorry about that. And then some other cardinals I like, both Penga's principle and extendable cardinals. But today we're just gonna be right in here. And so I want to show this diagram, and I want to show also Vika's diagram next, because it's like, this is like a painting or something where you zoom in and you see, oh, it's much more complicated than you might imagine. And I'm sure as people do more research, we're gonna get more pictures like this. And so this was zooming in kind of on the lower half between measurable and weakly compact. We can see there's a lot more going on. And so this project, maybe there'll be some diagrams like this, maybe not as complicated, but just showing like there can be a lot more variety going on between what's happening between measurable and strongly compact cardinals. And we have all these other kinds of complex relationships within the large cardinal hierarchy. Okay, so let me just zoom out a little bit on this so I can. Accidentally, okay, I think that works. Just let me know if you can't see it or something. So the open question that I'm gonna start with is, it's not the question that this talk is about, unfortunately, but it's an important question, and it's still open, but it's very much about the relationship between measurable and strongly compact cardinals. And the open question is there a model of ZFC where the first omega many measurable cardinals are the first omega many strongly compact cardinals? And so maybe if someone's watching, maybe you can think of an idea. If you don't have time this week, maybe next week when I give them the rest of my talk. But this has been going on for a long time. And so this is very vague dates here, because you never know when someone publishes something or comes up with it. But so let's just, some of the progress I think towards this problem is Manasseh's result in around 1974. If alpha is less than kappa, and kappa is the alpha measurable limit of strongly compact cardinals, then kappa is strongly compact, but not 2 to the kappa strongly compact, super compact. Okay, so this is talking about the relationship between strongly compact and measurable, and how we can have these two tied together, but not have super compactness there. Magador's identity crisis. A lot of this talk is about Magador's identity crisis because I really like love that paper, and also just some of the ideas came from that paper. Okay, and so another we'll see some of that. So there's more to say on that for sure that I'm going to say in this talk. In the 1980s, Magador proved that the first n-many measurables can be the first n-many strongly compacts. And this was a question that was open in his 1976 paper that he solved himself. And after inshallah, this had in 1997 had a generalization of Manas's result that the least measurable limit of strongly compacts is a little super compact. And this is an exciting kind of result that in the 80s, Arthur thought about this and proved this, and also Wooden recently got interested, and they were talking independently. They came to the conclusion that the result that the first omega many measurables is the first omega many strongly compacts does hold in a model of ZFC without replacement. Does anyone have any questions or anything?
Yeah. Well,
yeah.
What was the after Shala result from 1997?
Yeah, maybe I can't remember the exact statement of the result. Maybe Arthur can.
Okay, so the result is as follows. So in that 97 transactions paper, what we get, that's where it's published. What we get, we start with a model, we start from a supercompact limit of supercompacts, although you can use less than that, and we get a model in which the least measurable limit of supercompacts is the same as the least measurable limit of strongly compacts. The strongly compacts and supercompacts coincide below that, and at that measurable limit kappa, let us say that 2 to the kappa is kappa double plus, and kappa is kappa plus supercompact. So, but you can have 2 to the kappa is kappa plus 3. 2 to the kappa is, subject to some minor technical restrictions. Basically, whatever 2 to the kappa is, kappa will be less than 2 to the kappa supercompact, and the least measurable limit of supercompacts and strongly compacts, and the supercompacts and strongly compacts coincide below. That's the result.
Good, thank you.
Okay.
So it's a consistency result. It's not a. It's kind of different from Manas's result, then, is it?
That's right. It's a relative consistency result. That's exactly right. Manas's result is a ZFC result, and and the result that Saharon and I get is relative consistency. That's right.
Okay.
Okay, thank you, Arthur, and thank you for the question. Okay, so what do we know about strongly compacts, measurables, and supercompacts? Well, we do know that the first supercompact cannot be the first measurable. The first supercompact cardinal is a limit of measurables. So it excludes that possibility or that relationship. And so Magador says in his paper, what about strongly compact? Is the definition equivalent to measurable? And this is posed by Kiesler and Tarski. Is the definition of strongly compact equivalent to that of supercompact? And that was posed by Reinhardt and Solvay. So we have some results. It is consistent to have a measurable, which is not strongly compact. So measurable and strongly compact are not equivalent. Okay. And Kunin showed that measurable and strongly compact are not equiconsistent either. He showed that if there's a universe where there exists a strongly compact cardinal, there's a universe with many measurable cardinals. So maybe this is evidence against the open problem, I don't know. Manas proved that under the assumption of an extendable cardinal, there are many strongly compact cardinals which are not supercompact. And it's consistent that the first strongly compact cardinal is not the first supercompact cardinal. So we have more separation between these definitions. Okay, so Magador, he calls it a singular point in the large cardinal hierarchy, this bizarre behavior of strongly compact cardinals, singular. And this is what Magador proved in his paper. The first thing that he proved that is if it's consistent to assume the existence of a strongly compact cardinal, then it's consistent to assume that the first strongly compact is the first measurable. So this is like the first layer of that open question. And we're going to talk about the proof. But Magador also proves if it's consistent to assume the existence of a supercompact cardinal, then it's consistent to assume that that it's the first strongly compact. So there's the identity crisis. The first measurable can be the first strongly compact, but the first strongly compact can also be the first supercompact. But supercompact and measurable can't be the same. So this is an identity crisis. Okay, so the following questions were open then in 1976, and he asked them in his paper, this is his wording, does the consistency of strongly compact cardinals imply the consistency of supercompact cardinals? Okay, and that's still open. And by the way, I'm going to get to the definitions of strongly compact and measurable after I do have all this. So what about the second, third strongly compact? Can it be the second, third measurable? And he solved this, Magador. So let's go to the definitions, and then we'll talk a little bit about some of Magador's proofs. Yeah, go ahead.
What I'm going to do for recess.
Okay.
When I get there.
Uh-huh.
Because I'm going to assume that high in sign language is just like.
Good question.
Uh-huh.
I'm going to do, and then.
And Jonas, maybe could you mute your mic?
Oh yeah, sorry about that. Didn't realize I was on. Hi everybody.
Hey,
Hi.
Jonas, thanks for coming.
It looks like I'm that guy. Sorry, here.
Looks like what? Okay. Okay, so let's. Okay, an uncountable cardinal kappa is measurable if there exists a kappa complete non-principal ultrafilter U on kappa. So this is my image of the set kappa. And a filter is like a filter, that like your coffee filter. It's going to catch some things and let some things go through. There has to be some holes, because otherwise you could capture the empty set. But I think of this as an ultrafilter because it's extending. It can catch or not catch any of the sets in kappa. And so we have another definition of measurable. Suppose kappa is measurable by a measure mu, then the corresponding ultrapower embedding J from V to M sub mu by measure mu is an elementary embedding with critical point kappa. Also, if kappa is the critical point of a non-trivial elementary embedding, then it is measurable. Thus, another characterization of measurable cardinals is the following embedding definition. Kappa is measurable if and only if it's the critical point of an elementary embedding J from V to M in V. So that's often how I think of measurable cardinals, as the critical point of an elementary embedding. And here's the classic picture of that. It's the first point that's moved by J. And now I want to talk about Mitchell rank. And so we can talk about this like using ultra powers. I'm going to kind of try to cut to the chase. If kappa is not measurable, then the order of kappa is 0. A cardinal kappa is measurable if and only if its Mitchell rank is greater than or equal to 1. So here's a picture of Mitchell rank greater than or equal to 2. A cardinal kappa has O of kappa greater than or equal to 2 if and only if there's a normal measure on kappa which concentrates on measurable cardinals. So the measurable cardinals get caught in the filter, and below kappa, there's ultrafilter. You can think there's ultrafilter many measurables. There's many measurables below a degree 2, measurable cardinal Mitchell rank 2. A cardinal kappa has Mitchell rank greater than or equal to 3 if and only if there's a normal measure on kappa which concentrates on measurable cardinals with Mitchell order 2. So the cardinals less than kappa, which are Mitchell rank 2, get caught in the filter. Or you can think that there's ultrafilter many cardinals of Mitchell rank 2 below kappa. And this is for arbitrary Mitchell rank. A cardinal kappa has Mitchell rank greater than or equal to alpha if and only if for every beta less than alpha, there's a normal measure on kappa which concentrates on measurable cardinals of order beta. So for every beta less than alpha, there's a mu which concentrates on measurable cardinals of Mitchell rank beta. Or you can think there's a lot of for every alpha, beta less than alpha, there's a lot of cardinals of Mitchell rank beta below kappa. So we see the definition of strongly compact. An uncountable cardinal kappa is strongly compact if for any set S, every kappa complete filter on S can be extended to a kappa complete ultrafilter on S. So with it's oh, here's oh no, how did that get there? Oh, whoops, sorry. Oh, I feel like I'm missing a few slides. That's probably what happened. Oh man. Okay, let me just open something real quick. Sorry guys. Okay, I'm gonna stop this just for a second. I'm sorry. Okay. Just one second. Okay. Okay, let me just try something. Technicality on the text. So sorry, I'm missing I'm missing a picture that goes with this one, and then the definition in words that goes with the other picture. So I'll just say it. But anyway, a strongly compact cardinal. So it's very similar to measurable cardinals. But measurable cardinals already have the ultrafilter. So I kind of think of it like strongly compact cardinals, for every kappa complete ultrafilter, it gets extended to a kappa complete filter, it gets extended to a kappa complete ultrafilter. So an analogy that I think of is like measurable cardinals are like bread that's already done, it's already bread that exists, whereas strongly compact cardinals are this really amazing dough that's guaranteed to rise and become bread. So they seem very similar. Okay, so sorry about that. This is the other definition of strongly compact. And it says for every T, such that, so we have this elementary embedding, kappa is the critical point, theta is above kappa. So for every T, for every set in subset of M, such that V thinks that the size of T is less than theta, then there's an S such that M thinks that the size of S is less than J of kappa. So somehow M is thinking like all of these sets in here are below J of Okay, I'm sorry I don't have the definition of that. An equivalent definition of strongly compact is that there's a fine measure on p kappa theta. Okay. An uncountable cardinal kappa is strongly compact if and only if it is theta strongly compact for every theta greater than kappa. And this was the definition of theta strongly compact, sorry. Okay, and then kappa is strongly compact if it's theta strongly compact for every theta greater than kappa. So Magador used an iteration of prick forcing to make the measurables below a strongly compact cardinal have cofinality omega, thus killing their measurability. So that in the forcing extension, the first strongly compact is the first measurable, and this is the kind of forcing iteration that we're going to use in our proofs. Okay, and so amazingly, this is not what the talk is about, but I really liked this proof in Magador's paper, and so this is an outline of showing that the first strongly compact can be the first super compact. So amazingly, though this is not what the talk is about, Solovay proved that every singular strong limit above a strongly compact cardinal has the GCH. So with silver, we can find a universe with a super compact cardinal with unboundedly many measurables below violating GCH. While preserving that kappa is super compact. With a generalized prick forcing, we force these measurables to have cofinality omega, thus killing their measurability while still preserving their violation of GCH by not collapsing cardinals, while also being strong limits. By Solovay, then, there are no strongly compact cardinals below kappa because of Solovay's result there. In the forcing extension, kappa is still super compact and is also the first strongly compact cardinal. And the reason that it's super compact is because these measurables are sufficiently spaced out. So I don't exactly know, to be honest, but this is basically the outline of Magador's other proof in his paper that I want to talk about. And I just think it's amazing to have this Solovay prove that every singular strong limit above a strongly compact cardinal has the GCH, that somehow the GCH has to do with these like limits above strongly compact cardinals. Okay. So ultimate L in the open problem, this is kind of an anecdote. So does Wooden's ultimate L have anything to do with the open problem? So originally, no. When people asked him, but maybe more recent work may suggest otherwise. I don't know. We'll have to ask him. Okay, I feel like I'm gonna have a lot of extra time, or I can go into the next stuff, but let's just see. Okay, so the forcings that we need for the main theorems, Magador's prick iteration. So this is an iteration of prick forcing with finite support in the stems and full support in the measure one sets. And it's an iteration. Okay, and Magador's non-reflecting stationary set iteration, and this is as presented by Apter and Cummings. They published his result. Adding a non-reflecting stationary set of ordinals of some fixed small relative to kappa cofinality to measurables below kappa. So we're going to add non-reflecting stationary sets of some smaller
Sorry,
cofinality.
Erin, did you say what your main theorems are? Or?
No, I did. That's in the next slide. So
okay.
I'm sorry.
Okay.
And then we will, yeah. So maybe I can should go forward. Okay. So these are the main theorems, okay, which I plan to talk about next time mostly. The first is there's a universe where kappa is the least strongly compact cardinal and has Mitchell rank 2, and it's the least of this degree. So it's the order of kappa is 2, and it's the least strongly compact. Okay, and then this result for any increasing class of measurables, there's a forcing extension where kappa I is the ith measurable cardinal for I in I. So you can take any class of measurables and make them be the first however many measurables. So we can see that in the open problem, if we could just do this, if we could just take whatever set of strongly compacts and make them the first omega many measurables or however many measurables, the problem is preserving the strongly compact cardinals. And so in this proof that it would kill the strong compactness. Okay, the other another theorem is that there's a universe where kappa 1 and kappa 2 are the first and second strongly compact cardinals respectively, where the order of kappa 1 is 2 and is the least of this degree. And kappa 2, and the order of kappa 2 is 1, and kappa 2 is the least of this degree above kappa 2, and there's no delta Mitchell rank 2 between kappa 1 and kappa 2. So in other words, kappa 2 is the least measurable above kappa 2. And then we have this is what we call the descending case. As we go up, the numbers are descending. And the other theorem that's similar to this one is the ascending case, and that's that there's a universe where kappa 1 and kappa 2 are the first and second strongly compact cardinals respectively, where the order of kappa 1 is 1 and it's the least measurable, and the order of kappa 2 is 2 and it's the least of degree 2. And there should be some degree 1 in here, but there's no degree 2. This is the least. Okay. And we can actually get arbitrarily high, finitely much arbitrarily high for the descending case. So this doesn't say everything, but let me just say it more precisely, that for any kappa less than omega, there's a universe where kappa I for I less than k is the ith least strongly compact cardinal with, these are their Mitchell ranks. And then it's like this ascending case here. So the order of kappa 0 is k plus 1. Order of kappa 1 is k, and then there's no degree k cardinals between kappa 0 and kappa 1. So it's the least of degree k above kappa 0. And then you can keep going and get all the way to that the kth strongly compact cardinal has a Mitchell rank 1. And we'll see that we might hope to get a similar like ascending case here, where we can get the order of kappa 1 is 1, the order of kappa 2 is 2, the order of kappa 3 is 3, and so on. But this is actually really difficult, and it's maybe as difficult as the open problem. Okay, so let me go back to the forcings again, maybe. So we're using, Magador had good proofs in his paper because he was able to preserve like strong compactness when he did what he did. Okay, so sorry guys, I guess I went kind of fast. So I don't know if you want me to keep going or if there's some questions.
Just one small question. So it looks to me like instead of forcing to produce models like this, you could use iterations in some cases. Like if you're only interested in relative consistencies there. Like for example, if you want to make sure, if you're given this increasing class of measurables and you want to produce a model where these are exactly the measurable cardinals, I think you could just iterate away the ones that you don't want to be measurable anymore, and it looks to me like reducing the rank, like the Mitchell rank, you could also achieve by forming iterations, no? I mean, applying the measures, like if you have a measure 2, I mean, a Mitchell order 2 measure and you apply it, then that measurable cardinal will now have Mitchell rank 1, right? And so it just, did you guys think about that? I mean, is that?
I'm not sure exactly, I guess.
How do you propose preserving strong compactness this way?
Oh, I don't know. I mean, was this talking about, I mean, most of these results didn't seem to mention strong compactness.
Okay, if you're just talking about the ones that don't mention strong compactness, then I agree with you. You can do iterated ultrapowers, or you can also, I think, just construct the appropriate inner model. The point is, I think that there are
forcings
that do this, but what you're saying, I think, is absolutely correct, either via iterated ultrapowers or just construct L of the appropriate sequence of measures, let's say.
Mhm.
So.
Okay, yeah.
For this
All right.
one.
You can also do like Magador's identity crisis result by iterating. There's an old paper by Mitchell called, I don't know, Indiscernible Skies and Ideals, where he builds it's basically the same model, but you create the generic by iterating some measures.
For something like you said for which theorem?
For making all the Perkey sequences for Magador's first theorem.
Okay.
Making the least measurable the least strongly.
Okay. So
Can I ask a naive question? So,
yeah.
so what do you mean by universe, and what are these theorems in? I mean, I guess they're not ZFC, because I can see you say that or maybe it is ZFC. I don't know.
Yeah, I'd say ZFC. It's a model of ZFC.
Well, so you can prove in ZFC that there's a universe where there are strongly compact cardinals.
Oh, I see. Oh, I see. So we have ZFC. We need we do need super compact cardinal for some of these theorems, and generally, yeah, okay. We generally start in like a short universe.
These are relative consistency results. Con ZFC plus there's a strongly compact implies con ZFC plus the least strongly compact is the least measurable. Con ZFC plus there is a super compact implies con ZFC plus the least super compact is the least strongly compact. And these theorems are proven starting in a model of ZFC. We're always working as our base theory ZFC.
Okay.
For the last item on the slide, what are the consistency assumptions that you need to get that? I mean, you obviously need, I guess, K+1 strongly compact cardinals, but presumably you need something more than that, right?
You need super compacts, actually. The way the proofs are going to work is that you're going to need finitely many super compact cardinals. You can't, I mean, unless there's some way of taking finitely many strongly compacts and producing finitely many super compacts, which of course could still conceivably be possible. With what we know now, you have to start with finitely many super compacts and then do the appropriate forcing.
And then presumably the super compacts that you start with are going to be these kappa sub i's in the conclusion, right?
Exactly, that's right.
Yes, thank you. So, are there any more questions, or I could get started a little bit on the next part of the talk?
I can ask a question, sort of a semi-historical question, as is my wont. Remember back in the 80s, Patrick Dornois, he was in New York because he was working with Joan Berman on knot theory.
Mhm.
And he told me that the combinatorics of measurable cardinals were actually mapped nicely onto the combinatorics of knots. Oh, well, no, not knots, string, no, knots, yeah, braids. That's what it was, braid groups, that it mapped onto braid groups. Has anything like that happened for other kinds of large cardinals?
Well, you have the correspondence between braid groups and large cardinals only happens in the rank and trank level and a little less in the n huge level.
Uh-huh.
So it happens much higher on the large cardinal hierarchy, and still the correspondence is a rather weak correspondence because the main result says that you can have a free self-distributive algebra arising from both the braid groups and from the rank and trank embeddings, but right now the theory has not been developed to a point where there's too much of a correspondence between braid groups and algebras of elementary embeddings. That's something that still needs to be developed more.
Thank you.
Joseph? Okay. I feel like I should go forward a little bit, Zoe. Just a little bit. Does that sound okay, you guys?
Sure, there's plenty of time. I mean,
Yeah,
Okay.
I think you can either end here and just because it's a natural place to end and continue next time because I think you're at half your slides, or you can go on a little bit, whatever you like, Erin.
Okay. I feel like I
Erin, did you want me to make that comment that we discussed about Magidor's proof of the least the consistency of the least super compact being the least strongly compact?
Sure.
So-
And maybe you can talk about that you had talked to Wooden about his work, maybe, if you want.
Okay, well,
Okay.
so the remark about the original Magidor proof that of the consistency, the relative consistency from a supercompact, that the least supercompact can be the least strongly compact, is that the measurables that you would need to force to violate GCH have to be sufficiently spaced apart. You can't you don't want this. I mean, you could. Yes, you could do it. You could force it for all. You could force all measurables below to violate GCH and add kappa as well. But you don't want to kill them because you want to preserve supercompactness. So you have to space apart the measurables that you need to kill. And one way of doing it, this is not in the identity crisis paper, but this is maybe a more modern approach, is that the measurables that you kill via the Prickry iteration, let's say, could be all strong cardinals below the supercompact kappa, which are not themselves limits of strong cardinals. So you have a discrete set of strong cardinals, let's say below kappa, discrete unbounded set of strong cardinals, add the Prickly sequences to those, and that's going to be sufficient to destroy the strongly compacts below by Solovey's theorem and preserve the supercompactors of kappa. Another remark that one can make is that it's not necessary to have violations of GCH. You can actually prove this theorem by forcing over a model of GCH. And what you do is you can just iterate the Prickly forcing in the Magidor style over the same base set, the strong cardinals, which are not themselves limits of strong cardinals. And what you're going to do is you're going to add below kappa unboundedly many non-reflecting stationary, or unboundedly many cardinals, which have non-reflecting stationary sets of ordinals of cofinality omega. And then you don't have any strongly compacts below, again, by a theorem of Solovay. Erin's going to mention this later in her talk. Theorem 4.8 from Solovay-Reinhardt cardinality, that if you have a strongly compact, then every stationary set of small cofinality, that is cofinality below kappa, kappa the strongly compact, is got to reflect, but you've added all these non-reflecting stationary sets. So that's one remark about this. And the other thing about the observation that I made many years ago, and then when Wooden and I started corresponding about this in 2019, he made it independently, is that, and I'm not sure he came up with his proof, but the proof that I came up with is going to actually be a generalization of some stuff that Erin is going to speak about. So maybe I'll come back to it after Erin has presented more of the proofs. But basically what you can do is you can observe that some technique, either Magidor's techniques or however Wooden observed this, allows you to get a model in which the first omega strongly compacts are the first omega measurables, but it is most assuredly not a model of ZFC. Replacement fails. The measurable cardinals in that model form a proper class. So the function f from omega into the measurable cardinals, f of n is the nth measurable cardinal, is produces a proper class. So the range of that function on the set omega is a proper class. So replacement is going to fail. Anyway, but I can say more about that proof, I think, at least the way that I know it. I think I should let Erin give her proofs maybe next week or whenever she presents them. And then I'll say, I think, a little bit more about how the proof would go. I think that's what makes more sense, if that's amenable to everybody.
Okay.
And I come back to the first remark where you use strong cardinals that are not limits of strong cardinals.
Mm-hmm.
So I guess my first reaction, thinking about how you might do this is, oh, you want something reasonably sparse, use measurable cardinals that are not limits of measurable cardinals. And presumably if that worked, you wouldn't be doing the strong stuff. So why is strong important and why won't measurable do the job?
Oh, okay. So so the reason that I'm saying strongs which aren't limits of strongs is I want to work in a universe with no restrictions on the large cardinal structure. So if I started with a universe where you have kappa is super compact and you have measurables above kappa, then and you have measurables above kappa, if you do at least the iteration of, not the Prickrey iteration, but if you do the iteration of non-reflecting stationary sets, then what's going to happen is you're going to have to kill those measurables above kappa in order to preserve strong compactness. But if you take strongs which aren't limits of strongs, here's how it's going to work. So then you have some lambda greater than kappa, and you take a lambda you're starting with a supercompact, you take a lambda supercompactness embedding such that kappa is not lambda supercompact in the target model M. But then you can show that in the half open interval, open at kappa and closed at lambda, there are no strong cardinals. So, because if there were, then you'd be super compact up to a strong, and hence you'd be super compact, contradiction. So there are no strong cardinals. So kappa kappa will be strong there, but it's going to be a limit of strongs. So you're not going to kill that. So if you do either the prickly iteration or the non-reflecting stationary set iteration, whatever, you don't kill kappa. You don't kill anything between kappa and lambda. The next stage of forcing is well above lambda, and you can either, if it's iterating non-reflecting stationary sets, you can either lift the embedding by standard techniques to a lambda supercompactness embedding, or if you're doing the Magidor iteration or other iterations, you can extend the supercompactness ultrafilter, which generates the embedding. So,
Okay, thank you.
so I think, Andreas, that if you wanted to do a restricted sized universe and say no measurables above, that probably what you said, measurables which aren't limits of measurables, I think that would work. I don't think there would be a problem with that. But I think what we're doing here is we want to have an unrestricted sized universe. That's the key.
But could you just do measurables that aren't limits of measurables and such that nothing below them is super compact up to them? I
haven't thought about it. I think that's probably going to work. I mean, there are many different ways of defining this. I forget how Magidor defines it in the original paper, but you can pick lots of different sets. And what you just suggested, Gabe, I think is probably going to work. I mean, that sounds like it's something that should be okay.
Okay, other questions or comments? Okay. Well, let's just a little bit into the next, I guess. So this is just for the names of the theorems. So we'll get into it next time, and maybe we'll just do a more detailed proofs next time. But just for the names of the theorems, we have this idea of these straights, like these ascending and descending cases, but maybe it's a world where a straight in one direction is not the same probably as a straight in another direction. But that's just for the names, just for myself. But maybe we can just do this theorem. So I'll call this the ace of spades. This is Magidor's theorem. And, oh, well, we already know the proof of this. There exists a universe where kappa is the least strongly compact cardinal and has order of kappa 1 and is least of this degree, but that's what Magidor showed. The first strongly compact can be the first measurable. And this I call the ace of hearts. Okay, there's a universe where kappa is the least strongly compact cardinal and has degree 2 and is least of this degree. Okay, I'm just gonna give a proof outline, you guys, because we're kind of still talking about it. But I mean, I'm sure it's fine. But okay, so we start in a universe with a super compact cardinal and force the GCH if necessary, and start in a small universe. No order of delta 2 for delta greater than kappa. And this has to do with the prickly iteration. Okay, then we have to have this small universe. So use the Easton support iteration, adding a non-reflecting stationary set of cofinality omega to each delta less than kappa with order of deltas 2. Okay, so we're going to kill their measurability. So in my thesis, I did a lot of this, like, killing cardinals of any measurable degree to one specific degree. And so we get the order of kappa is 2 and its least of order kappa 2. By Magidor's unpublished results published by Apter and Cummings, kappa remains strongly compact. And there's no strongly compacts below kappa. So this type of forcing that we're going to do this with the other results, it's sort of a variation on this in between the the cardinals of interest. And also this proof, you could have any desired degree that you like. There's nothing really special about 2 in this case. Okay, so I guess I'm gonna stop there. But if there's any more questions, or we can even talk about some of the comments that were made earlier.
Actually, I think I'd like to get back to the remarks that Ken was making earlier. Just another historical remark. And this is found, I think, in the Magidor paper. He refers to an unpublished manuscript by Jacques Stern, and in which I believe the result is that the second strongly compact cardinal is not super compact. Now, I have absolutely no idea how Stern proved the theorem. I know how one would prove it now. I know what the Kimchi-Magidor techniques are, but there is this reference to this unpublished manuscript by Jacques Stern, and I have no idea where this manuscript is. I remember trying to get it, but was never able to get it, and it existed someplace, I guess. I don't know, Ken, if you know him, if you met him in Paris or where he was when he was thinking about this stuff, but he did. But this was a result that Magidor, I believe, credited to him. You have to unmute yourself, Ken.
No, Jacques is a brilliant guy and is capable of all sorts of magic off in the corner. I remember his talking. I remember talking about super compact cardinals and things. He probably just come back from his stay in Berkeley, where he worked some with Solove and whatnot. But then he did work in descriptive set theory. Ramez, of course, knows that. And but then went into cryptography. And now, or the last I heard, he was a powerhouse, a power in the French scientific research establishment.
Okay.
Okay, are there any further questions or comments, or how shall we do it? I mean, there were lots of questions and comments already.
Yes, thank you for all the questions and comments. And I have some questions about your comments. But
okay, then maybe we'll call this the end of the talk. I'll stop recording. Thanks for the talk.
okay.